This is one specific area of titrations which is related to formation of precipitates. 100 years ago, the textbook will give you literally hundreds of different reactions. These days, will limit to very few. However, one of most common is titration of sodium chloride with silver. When you titrate, solution becomes first clouded and then white precipitates form on the bottom. The reaction is silver nitrate plus sodium nitrate makes solid silver chloride and sodium nitrate, or in ionic form Ag plus Cl minus makes AgCl, colorless insoluble compound. When we write the reaction, for it we can write solubility product constant, which will be concentration of Ag plus multiplied by concentration of Cl minus. We are not looking at concentration of GCl because silver chloride is pure compound and it's solid, it's in separate phase. As usual, it's more convenient to use px function, which is negative log of x concentration, instead of just concentration. So PAG will be negative log of silver ion concentration. So what happens in our precipitation process? At the very first moment, first drops result is nothing. You are not reaching solubility product yet. Then more complex compounds are forming, including neutral molecules of AgCl, very few of them. Next, they start interacting, making assembly of several AgCl units that are soluble in water. As you can see, because we have more chloride than silver, all the surface of this entity is covered with Cl minus, and that's why it's highly charged. It has high negative charge and it's soluble in water. Next, these particles grow, so you have a GCl crystal inside, actually maybe multiple crystals, but still surface will be covered with chloride. Why? Because there is more chloride than silver, and the only common ion is Cl minus, so it will absorb on this surface. Negative particles, when they collide, they will repel each other. They cannot join each other because both of them have negative charge, and negative hates negative. Still, these particles are big enough so we can see the light scattered from them. Our solution is clouded. Next, when we are coming to equivalence point, number of silver ions and number of chloride ions is exactly the same. So there is no extra chloride on the surface left. In this case, several particles can easily collide and make a precipitate, cheese-like white precipitate, somehow similar of cheese formation. Now what's left in solution? It's sodium ions and nitrate ions. This process of forming precipitate from colloid we name coagulation. No chloride left in solution, no further precipitation is possible. Or when you titrate, you can see concentration of silver coming this way. First concentration of silver when you add it is very small because it's all precipitates with chloride. This concentration is described by solubility product, which we know. So, for example, if chloride is 10 to the negative 4, silver is 1.8 10 to the negative 6, and its product is 1.8 10 to the negative 10. So if I'm starting with 0.1 molar chloride, when I bring solution to chloride 10 to the negative 4, 99.9% of all my chloride is titrated. So very little chloride is left, and then if I add extra drop of silver, it instantaneously drops to stoichiometry, at which concentration of silver equal to concentration of chloride, and then I have over titration. If I have one extra drop of my silver, I have 10 to the negative 4 molar of silver. And between this point and this point, I have 2 orders of magnitude of silver concentration. So 10 to the negative 6 and 10 to the negative 4. It's a very sharp jump. Then concentration will change slowly when I'm adding more silver. So I can end my titration at any place here. I'll make no visible error. If I am going to silver iodide, solubility product is much smaller number, is around 10 to the negative 16. So if I am titrating my iodide to 99.9%, concentration of silver is still very small, 10 to the negative 12. If I over titrate it, I still can stop at my 10 to the negative 4. It's very sharp jump, very large in this case. And the reason is much lower solubility of silver iodide. Lower solubility is sharper is jump in concentration of silver. So when we compare all halogenides, chloride has reasonably visible jump, bromide has larger, and iodide has even larger. So why we are concerned about PAG? It appears that change of voltage, if we put one reference electrode and one silver electrode here, change of voltage is proportional to PAG. So instead of measuring PAG, we are simply measuring voltage, and when we see the jump of the voltage, we know that our titration is over. We do not even bother to calculate silver concentration. We just look at behavior of our voltmeter as indicator. This is the best approach for silver titration. Difference between iodide and chloride is so large that we can titrate iodide and chloride simultaneously. So if I'll have iodide only, I'll have this titration curve with a nice jump. But if I have chloride and iodide together, I'll have jump number one, all iodide is gone, and then jump number two, chloride is titrated. By careful analysis of these two positions, I can determine how many mils were spent on iodide ion and how many mils were spent on chloride ion. In some cases, we can do this titration without silver electrodes, and this is a so-called faience method or absorption indicator. What happens? When I'm titrating, at the first moment, my particles are negative. If my particles are negative, my indicator, which itself is negative ion, doesn't want to interact with them. Negative particles repel negative particles. So the color of solution is simply the color of indicator. Now, when I am done with my titration, the very first drop of additional silver will produce positive charge on the surface of my particle. Now, positively charged particles will attract negatively charged indicators. They will adsorb on the surface, and being adsorbed, they will change the color because they'll change their shape. When you're changing shape of molecule, you're changing the color. This change of color is more bright if you have fluorescence instead of absorption. And that's what we prefer. We prefer fluorescein, dichlorofluorescein, eosine, other fluorescent compound as adsorption indicators. What are uses of precipitation titrations? Mainly determination of chloride. 99% of precipitation titrations are chloride titrations. But if you want to titrate bromide, iodide, thiocyanate, cyanate, arsenate, cyanide, sulfide, you can do that. You can do even more exotic titrations like Borg hydride or potassium ions. Complicated procedure. But again, most common use is chloride.